Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera. Okay, in today's video session, we would like to continue discussing about wave propagating in a medium. So I think in my previous video, we have focused the discussion on the medium known as free space or perfect dielectric. So let's recap what we are doing now. Okay, so when we talk about propagation of wave, is more relevant to the field of communications, where we assuming the scenario of our discussion based on this, where we have a transmitter, which is an antenna. We like to investigate how actually a wave located very far away from the transmitter, which is at this particular position. Important, the distance from the antenna should be very, very far. So in order to support the statement of plane wave, so that's what we are doing. We want to understand how actually the wave is behaving at this particular positions, and then how we do it. We divide the medium, because medium is very important. In our earlier discussion, we are stated clearly the medium must be perfect dielectric. Okay, sometimes we can also name it to be as lossless dielectric. Okay, and then the same application can be used for the medium type known as free space. And we prove in our previous discussion, based on Maxwell equation and certain assumptions, that there are two main fields actually exist at this particular position, where the first type of field, we call it electric field. And then we able to derive the equation of electric field, which we are saying now equal to vector E. Okay, and then we call it to be E naught cos function omega t minus beta over omega z, x component, volt per meter. That is our final derivation that we have for electric field. And at the same time, we know at this particular position, it also contains the corresponding magnetic field, where we derive, or we prove that magnetic field actually is equal to E naught over impedance, cos function as well, omega t minus beta over omega z, but now it must have y component unit ampere per meter. So that is our conclusion that we able to do based on the derivation from Maxwell equations. Okay, so remember the discussion only focus on this medium. So let's plot the graph of E now. So let's do that. So I want to plot now the E pattern, which is the electric field, with respect to distance of propagations, which is Z. Okay, based on this term. So now what we can observe based on the equation, that the amplitude of the field remain constant. So if I plot the equation, my signal will have such a pattern. So what a bit illogical, we can see regardless where we are from the distance where we are from the antenna, whether we are close to the antenna or we are far from the antenna, we can observe based on this derivation, the amplitude remain constant. So this is something illogical in real world. Because why? As what we can experience as our handphone located further from the transmitter tower, we can sense that the power received by our handphone going to be smaller. So therefore, in terms of logical presentation, this scenario is illogical. Usually what is going to have should be this pattern, meaning that the amplitude should be becoming smaller and smaller as we move away from the source. So what should be the pattern of our field should actually adopting the red graph. So what I'm going to do in my presentation now to transform the idea of what we modeled before. Remember, the objective of our previous model just to develop the most simplistic versions, because we want to get the idea, the flow, how the derivation been determined. But now we're going to transform that paradigm from simplicity into more practical scenario. Okay, so therefore we want to transform now the discussion from the blue signal wave to become the red signal wave. So in order to make it simple, when we talk about wave propagations, okay, so there are very important parameters that we need to determine or we need to give. So that parameter is known as propagation constant. So I'm going to propose now a new parameter, so we call it propagation constant. So this constant actually enables us to derive or to define how wave propagate in any medium. So the symbol for this constant is given as gamma. So gamma is equal to alpha plus j beta. Okay, so now we have seen the beta being mentioned before as what we have shown here. Okay, and beta we define as what? In our previous discussion, we call it to be known as phase constant. In terms of equation, we prove that beta is equal to omega square root of mu epsilon. But we never see alpha symbol being stated before. So alpha is known as attenuation coefficient. So it's actually determine the slope of this graph, where the slope, how fast is decreasing or how slow is decreasing, will be affected by the value of alpha. And this particular envelope is defined as E naught exponential minus alpha z. So that's how the new term appear, which is more practical. Why? Because it can show that as you move further from the antenna, the amplitude of the wave that you receive at that particular position becoming smaller. The further you are from the antenna, the smaller the amplitude that you're going to receive. That is really corresponding to the parameter alpha, which is part of the complete parameter involved when we define how wave propagate, which is known as propagation constant. So now in my discussion here, I'm going to alter the medium. Okay, we're going to alter the medium instead from the scenario of perfect dielectric or lossless dielectric or even free space. We're going to go to other type of medium. So that should be our starting point when we want to transform from previous issue to our next issue. Okay, when we talk about medium, so we have seen medium been discussed before. So this is the medium where the wave is propagating. So what parameter that we use to characterize medium? Yes, in order to characterize medium, we use a parameter, we call it to be loss tangent. Remember? So we seen this been mentioned when we talk about displacement current density, where loss tangent is actually given as sigma over omega epsilon. So previously, if loss tangent equal to 0, we have seen the medium is known as perfect dielectric. Okay? Or what else? Lossless dielectric. Or even, yes, free space. So that's only true when we state that the loss tangent is equal to 0. And when the loss tangent not equal to 0, we have two different scenarios. So let's make it to be very small. Okay, so this will represent medium known as lossy dielectric. And if loss tangent also not equal to 0, but large or very large, so that will represent which medium? Good conductor. So when we involve in solving problem related to wave propagation, the first investigation we need to do is to determine which type of medium the wave is actually propagating. Okay, based on how? Based on using loss tangent equations. So by having this investigation, we can identify which medium it is, and then the consequence of this will determine what should be the corresponding gamma, which is what should be the corresponding propagation constant. Okay, so what I'm going to do now, I'm going to talk about the second medium, which is lossy dielectric. Okay, lossy dielectric. Okay. So what's special about lossy dielectric? Loss tangent very small. Yeah? So usually sigma not equal to 0 and very small. So let's say epsilon prime mu is equal to mu. Okay, that should be the parameter involved in lossy dielectric. So how actually we going to investigate the behavior of wave propagating in this medium? Any suggestions? So we have done the same process before when we in the world of perfect dielectric. So what should be our starting point to investigate how wave propagate in lossy dielectric? Good, using Maxwell equation. So let's derive that. So we're going to see now using from Maxwell equations. Okay, how many Maxwell equation? 4. Okay, let's define the Maxwell equation. Curl of E equal to minus dB over dt. Okay, that should be equation number 1, correct? What else? Okay, the curl of H equal to J plus dd over dt. That should be our second Maxwell equation. Okay, divergence of D equal to rho V. That should be Maxwell equation number 3. And finally, divergence of B equal to 0, Maxwell equation number 4. So that should be our typical Maxwell equation that we must start with, because that is the most general Maxwell equation without any assumption being made on them. Okay, so now we ask about the field now. So how actually we can define the field? So let the electric field being presented by this equation E. Okay, I'm going to put it E, and then should be E naught exponential minus gamma Z. So I'm using the term gamma here to define about the electric field. Okay, so if I put the vector, I'm going to put the term X. So that's indicate the field is in which component? X component. Yet it's propagating in which direction? Positive Z direction. So that's how we represent the electric fields. Okay, so now let's define equation of Maxwell here in terms of phasor form. Okay, so I'm going to explain what does it sense. Okay, so let's go. Now we are saying electric field going to be in X component. Therefore, what going to be happen to the magnetic field? So the corresponding H will be in which component? Okay, if E in the X component, the H going to be in which component? Y component. Why? Because we are in the world of plane wave. As what we have mentioned before, when we have plane wave, electric field and magnetic field are orthogonal to each other. So if E in the X component, the H must be in the Y component. Why? Because there will be no field in the axis of propagation, which is in this discussion the axis of propagation in the Z axis. So therefore H must always take into the Y axis. Okay, so that's been stated clearly. Okay, so let's define equation 1 now. Yeah. Okay, 1 now. I want to define 1 in more detail using these characteristics. Yeah. So what happened to the left hand side? So I'm going to solve it. X, because we are using Cartesian coordinate as what been argued before. To make it simple, d over dx, d over dy, d over dz. Okay, and then we know the E must only be in the X component, so EX, there's no Y component, no Z component. So that should be our typical substitution for the equation 1 on the left hand side. So when we solve this mathematics, what we're going to have in terms of X first, 0 minus 0, and then minus Y. Okay, I'm going to, should be 0 minus d e x over dz, correct? And then plus with the z should be 0 minus dex over dy, correct? That's what should be our simple derivation. So then we need to solve the mathematics. So we can see there's no y term in our equation of E, so this term will be becoming 0. Okay, that's done. So this is going to be, we're going to make it as it is because we cannot make it 0 because there's z term there, so less there. So that should be the solution that we are able to get. So on the right hand side, what happened to equation number 1? So it should be equal to minus mu d h over dt. So I can see clearly from this term, there's only y component appear on the left hand side. So therefore I'm going to state clearly straight away see the h will be only in terms of y component as well. Okay, I'm not bothered to talk about the x component of h and z component of h, because I can see based on the simple equation, the x term is equal to 0 and the z term is equal to 0. Okay, so therefore what I'm going to have for equation number 1 now, I'm going to have negative becoming positive. So d e x over dz equal to minus, okay, mu dhy over dt. Okay, so I'm going to convert this equation now into phasor. So what I meant by that is, we have seen before in our previous discussions, whenever we come across the term d over dt, because our field is sinusoidal, we can replace that term with j omega. Remember? That's been stated before. Yeah. So now, what should be the logical replacement for dz here? Okay. If d over dt, we can replace that with j omega. So what should be the replacement for d over dz? Okay, it's come from this term. So if I do the differentiations with respect to z, I can say to myself d over dz need to be replaced with what? Yes, minus gamma. Why we can do it? Because we are saying the field can be presented by these equations. So therefore, when we are encountering d over dz symbols, that symbol can be replaced with the minus gamma. So now our final equation that we end with is becoming gamma ex equal to, because now negative and negative becoming positive, correct? J omega mu h1. So this is our equation number 5. Okay, so now again, what is our objective? Our objective to define what should be the gamma for which medium? Lossy dielectric. How we able to do it? By starting with Maxwell equations. And then what we are doing, we just replace the general Maxwell equation with our specific derived parameter, which the electric field in the x component, magnetic field in the y component, and both field actually propagating along the z-axis, and the constant that we need to use in this explanation is the gamma, which is known as propagation constant. So that's equation number 5. I'm going to continue with equation number 2. So now equation number 2, we're going to repeat the same thing. Equation number 2. Okay, equation number 2 state what here? The curl of H. So I'm going to solve that matrix now. So X, Y, Z. Okay, that should be, and then d over dx, d over dy, d over dz. Now the h now should be in which component? We have defined that earlier. Good. In the y. So hy 0, 0. Okay, that should be our corresponding magnetic field. So if we solve this mathematics, what we're going to end with the x now, so should be 0 minus dhy over dz minus y, 0 minus 0 plus z dhy over dx minus 0. Okay, so let's substitute. So what is going to be our next step now, there's no x term, so this term will end with 0. So this should be something there. We're going to leave it as it is. So now we're going to see the only solution that appear is only x. Okay, so I'm going to rewrite that. Should be equal to, remember equation number 2, this term. What should be the j? The j sigma e, which e? Ex. Okay, and then plus epsilon. I can make it to be epsilon prime, or epsilon is okay. D over dt e x. Okay, so which component here? X component. Okay, that should be our steps then. So now let's convert into phasor form. So what we're going to have now, minus, so becoming positive, should be gamma hy should be equal to what else now? Sigma plus j omega epsilon e x. Equation number 6. Okay, so that should be our steps. Now we are converting from general form into phasor form. So now we have equation number 5, number 6, number 3, number 4 of Maxwell equations. So again, we have to remind ourselves we want to find what is gamma. Okay, determine gamma. That's all the objective now, to determine gamma. So how we do it? I think what we can do, we can rewrite equation number 5, number 6 to make it much simpler now. So let's rewrite equation number 5. Okay, equation 5 now. Okay, equation number 5. So what I'm going to say now, I'm going to give it to be Ex over Hy equal to 1. Okay, we have equation number 5. Ex over Hy should be equal to j omega and then mu over gamma. Do we agree on that? J omega mu over gamma, okay. And equation number 6. Okay, I'm going to say Ex over Hy now. Ex over Hy, so Ex over Hy. Again, Ex over Hy equal to gamma over j omega epsilon plus sigma. Okay. So that's our equation that we alter a bit. So again, remember what our objective to determine gamma. So I can straight away see now this equation actually the same. So therefore, I'm going to make it equal now. So by making equal, I can simplify further by saying now gamma square should be equal to, okay, j omega mu multiply with sigma plus j omega epsilon. Is it okay? Okay, I can rearrange the equation to be j omega squared and then mu epsilon 1 minus J sigma over omega epsilon. Is it valid? Okay, so again, remember what is our objective? To find gamma. So gamma, finally, is equal to J omega square root of mu epsilon square root of 1 minus J sigma over omega epsilon. So what we have to use here, we have to use only calculator. So once we use the calculator, what we can say that alpha, remember this is equal to what here? Alpha plus J beta is what we defined earlier. So alpha actually is the real component of gamma. So when we use calculator, we get the real component value, that is our alpha, and the beta now actually is the imaginary component of gamma. Okay, that's how I actually determine alpha and beta by using calculator based on the proof equation here. So the real number is representing my attenuation coefficient, and the imaginary number of the solution of propagation constant is my phase constant. Okay, that is how I actually determine alpha and beta. But anyhow, for those who want to see how actually Sadiku deduce further what is alpha and beta, so you can refer to page 490, section 10.3. Okay, if you refer to this particular page and section, you will see how Sadiku actually derived further. So he used this term, and then he used certain equations to state that actually alpha can be stated equal to omega square root of mu epsilon divided by 2 square root of 1 plus sigma over omega epsilon square, and then minus 1. Okay, that's what Sadiku proved. So he used this equation and some manipulation on the mathematical term. He ended with this detailed component of alpha equations. Remember, the unit here, okay, Nepper per meter. And then for the beta, you can see he proved to be equal about the same equation as alpha, but slightly different small change. So I'm going to show you the difference here. So 1 plus sigma over omega epsilon square plus 1, and then we know that the symbol, the unit for beta is radian per meter. Okay, so you can use either method, it's up to you. You can use the set equation shown by Sadiku, or you can use my proposed method by just use your calculator, and then from your calculator, the real solution you obtain is presenting your alpha, and the imaginary component of the solution should be our beta. And then you can test your solution using this formula to verify your results. So that should be what we stated before to understand how actually the wave is propagating. Yeah? So what is it? To determine this. Gamma, why? Because gamma is affected by the medium. Yeah? So you can see now if the lossy dielectric, that should be the gamma that we're going to use. And in this discussion, we purposely derive the gamma from the very basic method, which are using Maxwell equations. Okay, that is what you should be able to use to solve problem based on propagation of wave in a lossy medium. So what else we need to know regarding propagations? Good. Another thing that we need to know is impedance. Remember impedance? Impedance very important in propagation of wave because it's determine the matching, the flow of signal, the flow of power. If your system is matched, therefore the impedance must be same. So if the system is not matched, the impedance will be having not the same value. So I'm going to talk about impedance. Okay, impedance. What is impedance? Remember, impedance is actually equal to this symbol, and then we state before equal to EX positive over HY positive, or we can, for free space, equal to what? Mu over epsilon. That's what we end with in our discussion. The unit for impedance is ohm. So now the issue, what happened to the impedance in lossy dielectric? Okay. So if you look back into our equation that we stated before, which is this one. Okay, so this is actually impedance. And this also actually equal to impedance. Okay, so if I derive those things together, so what's going to happen here? So I'm going to have now, okay, impedance actually can be determined by dividing equation number 5 to equation number 6. That's what you can do. You divide equation number 5 to equation number 6. So you're going to end with this term. So let's do the divisions now. Equation number 5 divide equation number 6. Okay, so you can have EX over HY, that should be our left hand side, equal to mu HY divide with epsilon. Okay, I can to put 1 minus J sigma over omega epsilon. Which one? EX. Okay, so now what I'm going to have now, EX squared over HY squared going to be equal to mu over epsilon 1 minus J sigma over omega epsilon. So that's impedance, remember? So I'm going to say now, therefore, finally, my impedance, which is equal to EX over HY, going to be equal to mu, okay, over epsilon 1 minus J sigma over omega epsilon. Okay, unit so. Okay, that is our impedance. Or you can make it much nicer by stating this equal to square root of mu over epsilon divided with 1 minus J sigma over omega epsilon. So that is how we determine impedance for lossy medium. Okay, so that's one method to find impedance. Yeah? using our Maxwell equation, I can show you alternative methods. So what I mean by that, remember we obtained before impedance for lossless dielectric okay, we are said as before equal to mu over epsilon, remember? So now I want to use this equation as my foundation, but I want to adapt it for lossy. So if you want to convert equation that we developed for lossless to be applicable in lossy, what we need to do, remember, we need to convert, okay, so I'm going to write here from lossless, this had been discussed before, yeah, dielectric, so that now to be applicable for lossy dielectric. So the epsilon must be replaced with epsilon 1 minus j sigma over omega epsilon. So that's what we have stated before in our previous discussion under the category of displacement current density. So what happened here? So therefore now, for lossy, what we're going to say now, the impedance now will be exactly taken from this term, mu, but the epsilon now need to be replaced with this complex term, 1 minus j sigma over omega epsilon. And as what you can observe, so whatever we do here is exactly the same as what we did using basic method of Maxwell equations. Okay, so that's what. In EMT, there are many methods, and as I mentioned before, what we learned before actually still applicable in our current scenario. So this is what is happening. It's a proof to what been stated before. What we learned before still applicable in our current situation. So this is what can be used. But yet, what's important is to determine the impedance for lossy dielectric. Okay, so that's done. Okay, so I'm going to go further now. Okay, the detailed calculation, how to solve the problem, I believe that you can refer to our textbook. There are a lot of examples, a lot of questions that you can go through yourself. So in my lecture, I'd like to show you the process of getting those important parameters. For example, when you talk about wave propagation, it's very important to determine the medium first. And from the medium, we know that it's going to affect the wave propagation, and how we said that by looking at the important parameter describing how the wave propagate, which is the gamma. So now, alhamdulillah, we have completed our discussion regarding lossy. So I'm going to go for the last medium, conductor. Okay, so that should be our concern now, conductor medium. Medium now change into conductor. So how we'll be able to categorize that medium is a conductor? By looking at the loss tangent should be very large or large. So that should be the characteristic of our loss tangent. Once you identify that value to be large or very low or large, you can straight away conclude that the medium is a conductor. Okay, so how do I determine that? Now I'm going to look for what should be the gamma. So from lossy dielectric, we know that gamma is equal to j omega mu epsilon 1 minus j sigma over omega epsilon. Do we agree on that? Okay, that should be for lossy. So now for conductor, what we observe that the loss tangent is very large. Okay, what happened now? This term now becoming very large. Okay, so for conductor now, I can use the lossy equation but change slightly the parameter in that equation to become what now? Gamma now can be set equal to j omega mu epsilon, what else now? Yes, minus j sigma over omega epsilon. Okay, so what I can do here, I can convert, so I can solve the mathematics now. So let's convert the mathematics. Omega, I can cancel with the omega, good. Epsilon, yes, I can remove from our equations. So therefore, what I'm going to end now is equal to square root of omega mu sigma. Okay, so minus j I'm going to convert into polar form 45 degrees. Okay, so if I want to change into real imaginary, so it's become what now? Pi f mu sigma plus j pi f mu sigma. So for conductor, what we can conclude now, alpha will be equal to beta in terms of magnitude. And then that will be equal to square root of pi f mu sigma. So that's special unique behavior of conductor. When we propagate in a conductor, the value of attenuation constant is equal to the phase constant, which is not the case when the wave is propagating in a lossy dielectric. So that's a big difference in terms of propagation constant of a wave in a lossy compared to the wave propagating in a conductor. So that should be for conductor. So what else that need to know? The impedance. Okay. So the impedance, so I'm going to recall now, for lossy blue color, the impedance is equal to mu over epsilon 1 minus j sigma over omega epsilon. Remember that we derived just now. So we want to define what is the impedance for a conductor. Okay, so you can see this term now becoming dominant. Okay, so now for conductor, the impedance can be changed to become mu over epsilon. Now should be minus j sigma over omega epsilon. Okay, so when you manipulate, after you rearrange the equations, you can see the epsilon can be cancelled out. So what you're going to end with should be equal to omega mu over sigma. And then remember the angle here also 45 degrees. So that should be the impedance for conductor. So you can see the way I derive all these parameters come from the basic that we derived earlier, which from the lossy, and how we be able to derive all this from lossy using Maxwell equations. So I much prefer using this method compared to the set of equation that you can refer to table without knowing how that equation being derived, because that's will make the matter worse, because usually when you use equation to derive solution, you cannot explain the actual meaning of your solutions. You just know number without knowing what the consequence in terms of engineering application of it. Okay, so there you are. Okay, in my lecture today, as a conclusion, what we are doing, we want to know how actually a wave propagate in various medium. So there are three medium that we already stated before, okay, which are perfect dielectric, lossy dielectric, and conductor. So usually in the exam, they will only ask the first question as what we've seen before, knowing E field, how to find the corresponding H field. There are two methods that you can use, either again going back to Maxwell, or second method by utilizing the properties of plane wave characteristic. And then the second question is to find the properties of propagation constant. That's really related to type of medium that you are dealing with. Yeah? So with that, I think this is enough for me to talk about how we're propagating in medium. So inshallah, in my last video, I would like to talk about how to calculate the power, because actually what actually the element carried by this wave, energy, because this energy actually carry information, carry energy that you use a lot in to do a lot of day by day activities. So with regard to that issue, inshallah, in my last video, I'm going to explain how actually we're able to calculate energy from the derived wave model we are doing so far. Yeah? So with that, thank you very much. Inshallah, see you again in my last video. Assalamu alaikum warahmatullahi wabarakatuh.